A warm welcome to all. I'm Ms.A.Bhuvaneswari, Assistant Professor of Physics, Sita Lakshmi Ramaswamy College, Tiruchirappalli, Tamil Nadu, and I'm going to deliver a talk on nuclear fusion energy. Nuclear fusion. Fusion makes the universe shine and lights up all the stars, including our sun. Fusion occurs at extremely high temperatures and releases large amount of energy. It occurs continuously in our sun and the existing stars. Nuclear fusion is nothing but the process of fusing up of two or more lighter nuclei to form a heavier nuclei. During this fusion process, large amount of energy is released. The core temperature of our sun is 15 million degrees centigrade. At these very high temperatures, the existing two or more lighter hydrogen nuclei fuse together to form a helium nuclei. During this fusion process, large amount of energy is released in the form of radiations. Nuclear fusion energy. The fusion process releases tremendous amount of energy in the form of light and heat. The core temperature of the sun is 15 million degrees centigrade. The sun radiates the energy at the rate of 1026 joules per second. At these temperatures, hydrogen atoms, nuclei fuse together to form helium and it releases large amount of energy. Why are we interested in this nuclear fusion process? The world, particularly developing countries, needs a new energy source. The growth in our world population and growth in energy demand from increased industrialization and affluence will lead to an energy gap which will be increasingly difficult to fill with the fossil fuels. A coal power plant uses 9,000 tons of coal a day to produce 1,000 megawatts of energy and emits really very harmful pollutants including 30,000 tons of carbon dioxide. Even with efficiency improvements at the limit of technology, we would still need 40% of more energy and that is not available with the existing renewable sources. Because of the limited fossil fuels and there is a limited scope of renewable energy and there is a growth in the energy demand from increased industrialization also. So this fusion process will release high energy output and hereafter the worldwide we are focusing on the energy production with the help of the fusion process. So as I already told you, the fusion process is nothing but the fusion of the two or more lighter nuclei to form a heavier nuclei. The most efficient fusion reaction is that the fusion of deuterium and tritium to form a helium nucleus. So this fusion reaction releases 17.6 mega electron volts of energy. For this fusion process to take place, we need the surrounding temperature should be greater than the 100 million degree Kelvin that is needed for the fusion to be take place on the earth. So when deuterium and tritium is joined, fused together, large amount of energy is released along with the formation of the product nucleus called helium and few neutrons is also emitted. Now we are going to discuss the raw materials available for the fusion process on Earth. Tritium is an isotope of hydrogen which has two neutrons. It does not occur naturally, but it can be, however, easily produced from the neutron bombardment of lithium, which is naturally abundant. Currently, accessible reserves of lithium could supply all the world's energy demands for more than 1,000 years. Deuterium is also another isotope of hydrogen, which has one neutron. Its abundance is approximately 33 gram of deuterium in every cubic meter of water. As water is available in plenty, so we have a whole lot of deuterium for the fusion process to take place. Controlled thermonuclear reactions. Fusion process since it requires a very high temperatures of the order of 10 power 8 Kelvin to fuse the atoms. This is because during the fusing process, there exists a Coulomb repulsive force between the like charged particles, that is the helium nuclei, because of similar charges. So in order to overcome these Coulomb repulsive force between these like charged atomic nuclei, we need to produce a very high temperatures in order to overcome these repulsive forces. So that's why fusion process is called a thermonuclear reaction. So at this very high temperatures, the atoms are completely stripped of their electrons, which means the atoms are completely ionized. So this completely ionized atoms is called the fourth state of matter, plasma. So plasma is the fourth state of matter. The matter contained in stars, sun and galaxies is in this plasma state. Plasma confinement. In a fusion reactor, holding the plasma away from the walls of the container is a very big problem. So, holding the plasma away from the walls of the reactor core for long enough for a fusion reaction to take place at a temperature of 10 power 8 Kelvin is a very big problem. But this problem may be solved by applying a very high magnetic field where it holds the plasma like a bottle holds a gas, within which this fusion process may take place smoothly and the energy production will take place. In stars, plasma particles are confined mainly by the gravity, and high plasma densities can be achieved. On Earth, hot dense plasmas can be confined in magnetic fields, namely magnetic confinement fusion and inertial confinement fusion process also. Magnetic confinement device. It appears in the first sight that no material container can confine the plasma because of the very high temperature at which the plasma is maintained, which the material walls cannot withstand. The important problem facing the confinement of plasma or the loss of energy of striking off the plasma particles on the walls. One way the plasma is cooled and energy is get rid of, and the next one is energy transfer from the plasma particles to the walls, which will begin to vaporize the walls of the container. So this problem may be solved by producing a very strong magnetic field which holds the plasma away from the wall, within which the fusion process may take place smoothly. This structure shows the magnetic fields caused by the charged particles to move in a spiral field around the magnetic field. That is called toroidal magnetic chamber. JET, the Joint European Torus (JET), is the largest magnetic fusion test device in the world, which is situated at Fulham Centre for Fusion Energy in UK. It was constructed in the year 1978 to 1983. This is the largest production energy project in the European Union fusion program. Figure shows the JET, the first fusion reactor on Earth, Joint European Torus, which was located at UK. In 1991, the first experiments with tritium were made, making JET the first reactor in the world to run on the production fuel of a 50 to 50 mix of tritium and deuterium. In the year 1997, JET set the record for the closest approach of scientific breakthrough when reaching the energy released during the fission process Q, the Q factor, that is 0.67, producing 16 megawatt of fusion power. This figure shows the structure of magnetic confinement device called TOKOMAT, that is toroidal magnetic chamber. Next, we are going to see the limitations that we are going to face with this nuclear fusion process on Earth. The cost of the production of that nuclear fusion energy and the experimental setup that needs very higher amount. And the energy required to initiate the process is also very high and need to contain the free electrons that were produced during the fusion process in a safer manner. That was a big problem. And at last, the conclusion. Fusion is the promising future energy source. The next generation fusion reactors are coming to close to break-even, having negligible negative impact. That is, fusion does not produce any harmful smoke, that is CO2. So this having negative impact on this surroundings, the nuclear fusion promises to be the best answer to our energy crisis. The worldwide nuclear power generation, with the help of various nuclear reactors, including using fission and fusion process, provides 20% of the world's electricity, and this nuclear power provides 70% of the world's total energy usages. There are 440 nuclear power reactors in 31 countries across the world. They produce a total of 351 billion watts of electricity. So all over the world, this fusion process, which will be a promising future energy source. So I conclude my session that nuclear fusion energy will be our best alternative source for satisfying our future energy demand. Thank you.